The talk today is covering a new product, which is taking a fresh look at how Hadoop has been done all along and how we can make it better. If any of you have worked with Hadoop, you will run into issues or have run into issues, have experienced some of the things we'll talk about, and then we take it from there, see what Cassandra brings to the table and what that means for Hadoop and what that means for us if you're going to use Brisk. If there are the Hadoop experts, we'll also do advanced Q&A. At the same time, I'll assume that we'll start from ground level and go from there. So Brisk is Hive, Hadoop, and Cassandra. How many of you have heard of Hive or Pig? Yeah, perfect. So same data analysis. So what Brisk does bring to the table is it brings Hive, Hadoop, and Cassandra to one spot. We've looked at our customers, we looked at different use cases within the field, and the gist of that we found was people were using the new NoSQL stores in conjunction with this parallel processing paradigm that MapReduce produces, including Hadoop, and then using Hive on top or Pig and trying to analyze data. So we found a perfect opportunity to bring them together, mesh them well so it scales, and that's kind of what the story of Brisk is. I'll go kind of the behind the scenes, how we actually pulled it off and what were the interesting design decisions in the second half, but initially I'll do some stage setup for Hadoop itself. So everyone has heard MapReduce, and MapReduce from the glory days of the first paper that came out of Google to today has kind of evolved, and we have a huge ecosystem of adoption around MapReduce. If you have large data sets and you can work on small pieces in parallel, so having large data sets, check, but you cannot break it down, then it's not a good circuit. But if you can actually break it down to small chunks and have it all run in parallel and make it work, you're in the right place. You could use Hadoop. Now, so going back to the key algorithm in the MapReduce, where you have a bunch of input, and then you have key values, and then you're able to transform those key values to an output key values. That's kind of your ideal, right? So that's the classic flow from the original papers, nothing new. This is another view at the same MapReduce algorithm for multi-core. Professor Kunle from Stanford has this where you could do parallel version of MapReduce. So you run more in-thread mappers are run in parallel. Here's a parallel execution view of how your task plays. Partition your data. You have a partitioning function that partitions your data, and then you do this nice little sort, group, and reduce. So that's your MapReduce classic Hadoop in action, right? How does it play when you actually run it? Yeah, you have lots of workers, you have a few master, and you map your data, reads, reduce. But that's your flow. I mean, that's how you get parallelism. That's why you've broken down your problem to a bunch of parallel maps, and you try to align them such that you can run them as much in parallel. You do the sort. So this is another view of the same MapReduce. Split the data, then have workers act on that. There's a master who manages all these. That's kind of we'll get back to pay a little attention to the master guy. We'll get back to that. You usually do a lot of local writes, but never do like a remote write. Mostly remote reads. So that's kind of the crux of the strength of this way of putting your data is that this is your input files. Run the map. Intermediate files. Reduce. Put the data together. Output files. That's your classic sequence, and I'm sure people have looked at this before. It's a rehash, but from the original Sanjay Gimawat paper. Here's the core pieces. How does Hadoop actually work inside? There's a job tracker, as we looked at. How do you manage this? It's a name node which portrays how do you manage your inodes and HDFS. The crux of the best use case for Hadoop is you write once and read many, right? So It's files that are once created, they don't need to be and written. You don't need to, and once you close them, you don't need to change them again. So it's kind of immutable past. So it's kind of a classic use case for immutable past, but and append only sorts, right? So it's a very cool, allows for getting outside the POSIX model of being able to change data quite frequently, renaming things quite frequently. So it allows you to do a lot of optimizations. What do you want to do? You want to move computation, not data. That's the other second design philosophy behind this whole space is you have a data centricity. So once you have data, don't necessarily have to move it around. Once you move, it's large data, moving it around is not efficient anymore. So you just move the computation to where the data is. And that's the whole philosophy. If you want to take one line, this would be it, is to move the data, move the logic towards where data is, if the data is large. And of course, for the small data pieces, you want to move data to the actual compute. So, double-clicking the HDFS architecture, the actual setup is you have a name node which is in charge of all your metadata, all your access to actual files. You have a bunch of data nodes where you store the real data, and you have access, read access from clients directly to there. When you do writes, you have replication involved between. So when you do a write, you replicate between the nodes. Classic distributed file system architecture, right? Everything is a block. So name node has a bunch of inodes, and then you have blocks that you can go and access. That's your classic, again, from the Hadoop paper on HDFS. Right? Data nodes do read and writes for blocks, so all your data is actually stored as real file system blocks. And the name node that's your single master node. That's your single machine address space. That's where you put all your data in. That's also your single point of failure. So the name node is all that we heard so far is very parallel, massively distributed. It's one of the single points of failures in the entire Hadoop ecosystem is the name node, because that's where you store all your inodes, and that's where you want to manage. It's all, again, since everyone has written code in Java, it's all written in Java. So it has the classic challenges of scaling up. So your Hadoop, the size of your Hadoop could also be limited by that. So managing a single large in-memory system is hard, and it's hard, and that's why we are in the parallel distributed mode today. That's where we are seeing the new revolution of large distributed stores, and that's why a single large node is always a problem. So that's where we focused our efforts on, and try and see most of our customers who would be running this would be spending a lot of time trying to duct tape the name node, trying to create a way to get it to stabilize. If that fails, you probably lost your entire jobs. All the jobs that are running could be lost at different stages. The recovery path from there is hard. And so that's, where in many sense, it's a single node and it needs to be distributed. Most people agree that the best way to do distributed computing is not do it at all, and unless you're really forced to do it. And in this case, we are, our customers ran into that, and so did a lot of the Hadoop customers, and there would be a lot of interesting challenges around it. And that's kind of where distributed name node, or how do you do a distributed name node, and that's kind of the nuances behind why Brisk, right? So, if you think about it pictorially, you have lots of data nodes doing your data blocks. The name node kept growing because you have all the metadata. And what Cassandra does, in some sense, is create one kind of node. There is no name node, or it's distributed across, just like a regular node. So that's kind of the before-after of Brisk. Like this is your Hadoop. You have data nodes and name nodes. In the future, we see one kind of node. So it's peer-to-peer. And so that's kind of your intro, and we'll discuss Cassandra at a little length as well. What is Cassandra? And some of you have heard of it, some of you have used it, but the crux of Cassandra is how do you get high-scale data stores that can run across lots and lots of machines, tolerate failure, and are still not losing data, still not losing accesses. So that's kind of your, and peer-to-peer has historically survived. Peer-to-peer as a philosophy, as a scaling methodology, as distributed computing techniques. I mean, we have all seen and lived the Napster revolution and P2P way of doing things, and peer-to-peer has survived, and it's distributed, really distributed. There's no master, there's no central anything, right? So Google created Bigtable. Amazon did Dynamo. Dynamo is this classic peer-to-peer operational model where you lay your data on lots and lots of files, lots of systems, and are able to use a kind of a loose consistency model and get high scale, right? At Facebook, circa 2008, these two combined, you get this. Bigtable has, how many of you have heard of Bigtable? Sure, so not much to explain there. Bigtable essentially gives you a column family-like semantics for addressing your data. So you get a schema of sorts, right? And Amazon gives you the classic Dynamo model of operational. The Dynamo is the classic operational model of simplicity where you can add lots of nodes. Actually, the same kind of techniques are being used in other models like SimpleDB and others. So Bigtable gives you that schema, and that's kind of what the nuance around Facebook invention, putting them together. It was open source, incubated, and then we have a few customers using it live in production, Netflix, one of them. How does it work, really? Cassandra has a ring structure to it, and every node is actually designated to a certain range of keys, right? So if you think of this as a big space, and you chunked each of them to different key sizes, to key ranges, if you now insert C, and so somewhere in between, so you pick node, so that's the node. Based on the key, you find the node to write your element to, and you can set for each of these writes how many copies you would like to see. You can set replication factor for every single write, right? So if there is something really classic, well done for NoSQL stores, that would be the replication model in Cassandra. I mean, that's one of the good strengths, right? Every store has their own strengths, and this one has a very nice property around replication. Now, you could set, so if you set 3 copies, the first copy is going here, then you have asynchronous, as soon as it finishes its write on F, so every node has a commit log and a kind of your in-memory representation. Once it writes to a commit log, it basically, it also asynchronously fires off 2 more replicas over these 2 other nodes which are participating in that replication. Now these 2 can, mind you, be in a different data center or a different Amazon region. They're asynchronous, and they're going to go finish those writes and have those copies ready for you in different geographies, right? So in some sense, you have, as a regular, simple 5 node, 6 node, or size customer, you can put them, so you can actually, there's a snitch which basically tells it to look up, it looks up a small list of items and says, okay, this needs to be in 2 different racks. Make sure they're in 2 different racks, so just in case there's power outage. So it automatically does that for you. Now, let's say one of these nodes actually down or did not respond. It actually makes a note on the node saying a hint, it leaves a hint there saying, replay this when that node comes back up, right? So it's tolerant to the failure. It also has a lot of interesting nuances around how, if this node is out of sync with other nodes, so the other So that's one, how do we get the replication work? The second piece, interesting piece here is, as you add nodes, typically, I mean, people who have used coherence or gigaspaces or other large systems, as you add nodes, the communication patterns between them, either it's TCP, UDP, or high, it's very, when one node goes down, it has to communicate with everybody else and tell I'm down now, right? Or remove the data or replicate, rate it around. The communication pattern in the Cassandra system is gossip based, which is a very lightweight exponential algorithm. When gossip actually works like real world gossip, where you go and tell, so every node gossips with a couple of nodes, neighboring nodes, and those nodes go and gossip with other gossip partners. So it's kind of like if every node participated in sends two nodes go and two. So you have a pretty large exponential algorithm. So in some sense, it's kind of amortized over the course of the entire size of the system. So in some sense, it's exponential, but at the same time not very expansive. So the communication between the nodes is independent. Is kind of a different. Is a mechanism that leads to a much more easier, well-breathed, well-growing system. But the reason we brought up the gossip piece was if there is actually any of the nodes out of sync, the data can be repaired. So as you do your reads, you can also, so when you pull the data out, when you do the reads, you can actually ask, I want just one of them. Let's say we added the data of this building. This building's geocodes are not changing anytime soon. They're going to be the same for pretty much history of the Earth. So we're probably going to, it's if you write once, you just can read it from anywhere. So if you write a copy of that node in 3 nodes, you can suddenly, your reads can get 3x the performance because they can hit any of these nodes and get an immediate result. So for the data that's very light, very non-changing, you can use a read consistency of just 1. For data that you want to make sure has higher reliability or higher correctness, you basically ensure that all nodes or the majority of the nodes are saying the same answer. So you can actually say quorum. So then you get 2 out of these 3 nodes returning with the right answer. Does that make sense? So in that sense, it is a tunable consistency model that as we have today, and that allows it to the end user to program it and learn and be able to not pay the same cost for every read, and which is true for today's reads, where you force yourself to pay the cost of asset for every read. Here you can actually say this data, the geocode data or the address data, the maps data is not going to change anytime soon. That data can be just R equal to 1. But for the data where you actually do need more consistency, you can enforce a higher consistency level, and that's the onus pushed onto the end user, end developers, and that's kind of the thing that we discussed earlier, which came out. But really, the crux of that is that it's up to the programmer to design which parts of the code can actually take advantage of a very high read performance or very high write. So the write performance of this, we just discussed the replication. The write performance is really, really very low. So Cassandra's real strengths shines when it does writes, really like orders of magnitude faster than the reads, and then it's usually single digit to early 2-digit milliseconds, and it's a durable write. It's not writing just to memory. Right? So, the write speed, of course, is based more so on the it's the commit log is append only. So when you do a write, there's a commit log that does append only sequential access to file. So in other words, every node has a commit log, as we discussed. So as soon as you send a write, a block is when you hang out a record here, append only, so it's sequential. So this thing is, as soon as it finishes, it allows the mem table copy to be read. Right at that point, it's already in memory, makes it available for reads. Also goes for the other copies. replication, reader, right? This is nothing out of the world. It's classic log structured data. It's what DB2 uses for commit logs, right? So it sits on the great advantages that were created in the database research. It's not something, so data is not lost, right? But the replication part, being asynchronous, allows you to scale on that front as well. What does big table do for, so we looked at the distribution model, that's the dynamo. So we're actually really talking about dynamo distribution model. We also know that big table brought something to the table, so that's this thing. So it's more of a dynamic column family model, which basically says you can have, like, so this is basically the tables, the column families are more non-uniform column structure. So you have a few columns that are, a few rows with 2 columns, a few rows with no columns, and a few rows with a lot of columns, right? So, so it kind of, how many of you have heard of the normal forms for databases? Few, right? So the first normal form is if you think about it in the commonsensical approach of first normal form, you go to the grocery, you make a list of things you want to buy, and you say milk, amount you want to buy, like, so everything you have, like item name and amount you want to buy. So you kind of expect, so if you find one of the rows with no amount you want to buy, you're worried because you need to find out that data needs to be filled up. That's you expect a structure for your data. But what if it's just, it's like, certain columns, certain data is not amenable to that structure all the time. You're wasting a lot of your, both your space and query performance focusing on having all the columns to be similar. And that's kind of all the rows to be similar. And that's kind of the idea behind this. But the beauty about this one is if you are designing such that you need to get only, that certain rows have enough data, you just go after that. And so this is showing the Brisk structure. And Cassandra FS, Cassandra node, we'll get back to this classic marketing slide, but we'll come back to this at some point. We looked at Cassandra. Brisk basically brings to the table ability to store Brisk data and Cassandra data in the same ring structure, right? So in some sense, it provides a way to write your Hadoop jobs as well as run the results of those data into the same Cassandra store, so you can then run queries off of it. Now we'll look further into how this works. Okay? The main things to remember is we had job tracker, task tracker. There's a bunch of nodes that are task trackers, and there's a single node that's job tracker. This is our op center that's showing the ring 20 nodes. Hadoop nodes are having the Hadoop in it, and that's the Cassandra side. So what we are seeing here is basically, historically, ETL, you would run Hadoop jobs on some other, on a HDFS store, and take those results, put it into a table that you can then serve the rest of your web app from. And that table, instead of being on MySQL and not scaling, can now that's where the NoSQL source came into play. And this one, you actually use the same cluster that you have, use it both for Brisk and for Cassandra, Hadoop and Cassandra. So with that, we'll get to your question: how does this thing work? Right? The core of it, we're using the Apache, soon to be Apache, Yahoo distribution, which has the security patches to it. Apache Hive, which is the query mechanism at the top that's running on top of this. Cassandra 08, which just got released, and a SQL interface and Drift. the column families that we widely discussed, how do we actually make this whole HDFS sit on Cassandra? Hadoop file system is its own mechanism. What we've done is basically use regular column families to write inodes and sblocks, right? Subblocks. Little code here. Create two complete column families onto the same key space Cassandra file system. So this is how we would write code for a Cassandra thrift client anyways. So very simple, nothing fancy, just completely good old-fashioned Cassandra file system. Cassandra column families. So nothing new, nothing out of the world. It's actually pretty dead simple once we started thinking about it. We're like, wow, why didn't we do this before? Subblocks, you can set the caches. So I show key cache size here. You can grow that if you think you can get better performance. You can set row cache on the inode to get a lot more in-memory performance for your inode column family. But that's the beauty behind it. It's just pretty good old-fashioned. It's run and maintained, operated and maintained just like a regular Cassandra column families. So all the discussion we had earlier pays off now. You know how it works. It's straightforward. It's well distributed, replicated, and uses the same pieces. So if you look at the actual distribution, how the data is actually going through the system, you have take a file, load it, basically has all the inodes, subblocks. Blocks are distributed across different nodes as just regular column families. That's the nitty-gritty of it. We actually worked with different performance sizes for these and came up with different sets that work very well for most of the benchmarks, as well as some of our customers were figuring out what's the best use case, best sizes, and so it's a new product in many ways. So we are making sure we understand how the end customer plays with it and get a good performance node around it. So Hadoop is really adding job tracker, task tracker, and all the other intelligent nuances around the MapReduce. And what we did is basically take those two and put it have every node have capability to run tasks, and one node today to run jobs. Brisk snitch, right? So how do I know what is a Cassandra node and what is a Brisk node? So snitch is the concept where, let's say you issued a write. It said, write this to a different EC2 region, right? I know that US East could crash, so I want to make a copy in US West, right? So we have a concept of EC2 snitch for that. So where you can actually, during your write, you can say what mechanism to use for, what snitch to use for is one other column in your actual write. So it actually goes and makes sure that the replica copy nodes will reside or fail the write, right? So what we did is piggyback on the same simple dynamic snitch, to use for Brisk versus Cassandra. So what we did here is, in the same ring, we've defined logically these are two different data centers. One is a Brisk data center, and so using the same simple snitch mechanism, we say, do you have tracker? Yes, I'm a tracker node. If it's a tracker node, we know it is a Hadoop node, essentially. So the same Cassandra nodes, whoever is a tracker, whether it's a job or task tracker, right? So he belongs to DC. If he does not have a tracker, then he must be a Cassandra regular node. So we just use the same mechanism. So everything is using the notion of, are you a tracker or not? One of the things that I was going to say is, you want to use your Hadoop to run, so a classic workflow, and that's one of the questions that, I didn't get your name, sorry. One of the questions Dan asked earlier was, why Cassandra, and why do I need to have a Brisk snitch, or why do I have a Brisk in the Cassandra side? So typical use cases, and there are more use cases that we are seeing customers use it, is people have a bunch of logs, machine-generated data, access logs that you want to process. You want to take that data and run a large Hadoop job on it and categorize where, for example, video analytics logs, right? You have all these click streams coming in from all the geographies. You want to run a Hadoop job and says, I hit so many from Europe. I hit so many from the US and all these states, right? So that's your typical use case. So you run this Hadoop job that runs on all these logs and gives the IP addresses, translates them, gets you the answer, right? Now you have this answer, and you know you have like a dozen different, like lots of customers wanting to serve this, look at this data right away in a web app, right? So that part, the second answers of this Hadoop job, you want to put in a high-scale store, right? So typically people would put it on a MySQL, shard it, or put it on Cassandra and run that part on Cassandra because they know that scales. So what this crux of the Brisk invention, if you will, is it brings them two together. You can now run the Brisk Hadoop jobs on one part of your cluster, and they can be busy all the time, continuously. Your logs, you're just uploading logs. It's running the Hadoop jobs here. And you scrape that data into the same cluster on the side. So you actually can have a Cassandra section inside, so you don't actually take the end result of this and put it into another data store, put it right here, and run your app from there. So in some sense, it reduces how many clusters you as a ops team or a design team have to maintain and different ways to manage them. So it's just one thing, and then you can increase the size, add bootstrap based on how you're using it. Does that make sense? So essentially, the end-to-end workflow, we looked at the end-to-end workflow and then figured out what is an interesting use case for it. So we looked at this niche, then there is Hive. So Hive presents a classic SQL-like access and to the whole Hadoop ecosystem, where you can run a big, large query, load data, run large query on the Hadoop stuff, right? Now, there is push-down predicates, which is coming up in beta 2, which is basically allows you to slice and cut down your slices and partition it up front. Now, here's a typical, and this is a very small select, by the way. That's usually you can do a large. This is part of the actual example on our website, so we want you to play with it after you're done. But basically, you can load data through a file and run a lot of queries, right? So here's where your question on how do I get joins in Cassandra? Use Hive, right? It's not the same. It's going to translate that select to a MapReduce job and come back rapidly, much faster than other ways. But there is no, since you never had a join, this is one of the first ways you can actually get some SQL-like access to the Cassandra ecosystem. Hive, again, is a project from Facebook, as most of you are aware of. So that's the gist of what we are trying to do, is to get you cross-data center support. And that's, I mean, historically, this was never available for ordinary people. High scale, like ordinary people as in financial services guys would do multi-data center or big companies, but you can do that with two nodes. You continue to use your Cassandra column families, Cassandra CFS, which is the column, the Cassandra file system. And at some future, ETL will completely become blended with real time. It's not there yet. It's near real time, but it's kind of the vision that we have. We're kind of getting there, but it's not there, right? Here's your job tracker using the Op Center. So when you run a Terra sort, you can actually see the progress. Kind of your, you still get your old job tracker. We don't take that away, but this is available to see progress. It's a huge team effort. All hands on deck. We basically, so around the turn of the spring, we had an announcement, want to go make Brisk happen, go make Hadoop happen. We integrated the entire team, pretty much all ends of it, made sure we're it's QA, done well, tested, documented, but that's the whole team. So none of this has been, it wasn't easy, but we made it happen. We have a large user base of Hector. We also have customers writing clients in non-Java. Like we also have the Picasa and PHP Casa, both of them are part of DataStax teams. So we also have Scala clients. C++ is not uncommon. We have customers who have used that. And people are not looked at the Thrift API where we created the tree space and the column family. That is the Thrift API. So it's convoluted, but it's there. It can be used. It's all Java. So in some sense, people are not. But it is, in some sense, that's the focus for us, is to make the API even simpler so it becomes easier. Here's a 100-node Brisk cluster that we ran during our tests. We kept it running for a long time, enough to run some good EC2 hours, but yeah, that's so the evolution continues. We have taken that initial Facebook Cassandra, now taken Hadoop Hive, we have Brisk. It's moving along to get you a much more robust stack. That's what once you have enough nuances, you're able to use it in a more solid fashion. So our job is to try and push the envelope there, see how the customer use cases play. Pig is now part of the same stuff, so you'll get the whole eventual stack, which you need to do data analysis. So, get started. It's open source. It's all Apache. Brisk is completely. We are encouraging a lot more work from the committers, from people, developers, users. Brisk AMI itself is available. The Wi-Fi here failed on us, but that was part of the demo as well. All right, so thank you.